In this video, we're going to look at another example of moments and centroids. Consider a lamina with constant density rho, whose boundary is formed by continuous functions y equals f of x, y equals g of x, with f of x larger or equal to g of x, and x equals a, x equals b. So let's start our analysis by looking at one of these rectangles, and then we're going to develop the formulas for the mass of the region, for the moment with respect to the y-axis, the moment with respect to the x-axis, and of course the centroid formulas x bar and y bar. So looking at this rectangle, so what we have is, let's draw this rectangle here. And here we have the x-axis. So the bottom part of the rectangle is where it meets the bottom function y equals g of x. And the top part is y equals f of x. And this part, the left endpoint is xi minus 1. The right endpoint is xi. If you average those, we get x bar. So there it is. This is x bar. And the y coordinate is going to be the average of the y values. So it's going to be 1/2 of f of x plus g of x. So let's put that in. So here we have xi bar. That's the average x-coordinate, so that's the x-coordinate of the center of mass of this rectangle, this arbitrary rectangle we've drawn, and the y-coordinate of the center of mass of this arbitrary rectangle is going to be 1/2 of f of xi bar plus g of xi bar. This is the centroid of this rectangle, basically. Now, if we apply the same Riemann sum arguments as before, we obtain the centroid integral formulas. Okay, so the mass is density times area. That's rho times the area is integral a to b, and the height is given by f of x minus g of x, the difference between the two functions, times dx. Looking at the diagram, that makes sense. This is f minus g here. That's the difference between, that's the height of this rectangle, times dx gives you the area of this rectangle. Then the integral basically adds up all these vertical slices. All right, let's look at the moment with respect to the y-axis. That's the integral from a to b. The distance to the y-axis is simply x times the mass of this rectangular element is rho times f of x minus g of x times dx. So x is the distance of the rectangle, the arbitrary rectangle, to the y-axis, and this is the mass of this rectangle. And of course, moment is always mass times distance. The integral adds up all of these moments. All right, let's now define the moment with respect to the x-axis. Integral a to b. And what is the average distance to the x-axis? That's given by the average of the two y values, 1/2 of f of x plus g of x, and the mass of this rectangular element, this slice, is rho times f of x minus g of x times dx. So let's label it. This part here is the mass of the rectangular element. Sorry, this part is the average distance of this rectangular element to the x-axis. So this is distance. And this part is the mass. Mass times distance gives us the moment, and the integral sums it all up. All right, so x bar, by definition, is a moment with respect to the y-axis divided by the mass. And the moment with respect to the y-axis is rho. Rho is a constant, comes out of the integral a to b, x times f of x minus g of x times dx, divided by the mass, which is rho, integral a to b, f of x minus g of x dx. Y bar is equal to mx divided by the mass. Now, what is the moment with respect to the x-axis? If you multiply these out, this is f of x plus g of x times f of x minus g of x. It's kind of like a minus b times a plus b. And what do we get when we multiply that out? We get a squared minus b squared, because the middle terms cancel out. So by the same reasoning, we get rho times integral a to b f of x squared minus g of x all squared dx divide by rho integral a to b f of x minus g of x dx. And you will notice that density, the constant density, cancels out. So that tells us that the center of mass, x bar and y bar, does not depend on the constant density and only depends on the geometry of the region. It only depends on the shape of the region that you have. So we have developed the integral centroid formulas. We can now apply them with an example. All right. So the question here is to find the centroid of the region bounded by y equals x squared, y equals 2x, with density rho is equal to 5. Now, I know that density cancels out, but with these questions, I always include the density because sometimes in the exam, they will ask you to compute the moment, say the moment with respect to the y-axis, then you have to include the density. All right. So the function we have is f of x. Let me change color here. F of x is equal to 2x. G of x is equal to x squared, and 2x is on top, and x squared is at the bottom. Let's find the intersection points. We make f equals g, so we get 2x equals x squared. Bring everything to one side and factorize. We get x squared minus 2x is equal to 0. X factor x out, x times x minus 2 is equal to 0. So we get x equals 0 and x equals 2. These are the x coordinates of the intersection points. We got x equals 0, x equals 2. We can plug this into either equation. I'll plug x equals 0 into f of x. F of x is equal to 2x. So we get y equals 2 times 0 is 0. And let's plug the x equals 2 into g of x. G of x is x squared. It doesn't matter which one you put it in. So we get y is equal to 2 squared is 4. So we get the intersection points 0, 0, and 2, 4. A little bit of basic math, basic skills. All right. So now let's apply the centroid formulas to find the center of mass. Let's start with the mass of the region. That's going to be density rho integral a to b times integral a to b f of x minus g of x dx. The density is 5. And the lower limit of integration, the lower x limit is 0, the upper x limit is 2, and top function is 2x, f of x is 2x, bottom function is x squared. Now we need to integrate this. Mass is equal to 5 times. Reversing the power rule, that's going to be 2x squared over 2, so we just get x squared. Minus an antiderivative of x squared is going to be add 1 to the exponent, divide by the same. We get x cubed, divide by 3. Evaluated from 0 to 2. So we get 5 times, put the upper limit in, we get 4 minus 8/3 minus, and now put the lower limit in, we get 0 minus 0. So we have 5 times, let's take common denominator. The common denominator is 3. 1 goes into 3 3 times. 3 times 4 is 12 minus 3 goes into 3. 1 times 12 minus 8, that's 4. 4 times 5, that's 20. Divide by 3. This is the mass. All right. Now let's find the moment with respect to the y-axis. The moment with respect to the y-axis is equal to rho times integral a to b x times f of x minus g of x dx. So the density is 5. Integral a to b from 0 to 2. Those are the x coordinates of intersection. X times f of x, which is 2x, minus g of x, which is x squared, dx. Let's integrate this and solve for the moment with respect to the y-axis. My, let's simplify the integrand, is equal to 5. Integral from 0 to 2. 2x times x, that gives us 2x cubed, minus x times x squared minus x cubed, dx. Now integrating, we obtain, what is the antiderivative of 2x cubed? That's going to be 2x to the 4th. Reversing the power rule, divide by 4. Minus antiderivative of x cubed is x to the 4th. Divide by 4. Now apply fundamental theorem of calculus. Evaluate from 0 to 2. So the moment with respect to the y-axis is 5 times. Putting the upper limit in, we get 2 to the 4th. 16 times 2 is 32 over 4. That's, I guess, going to be, we get 2 to the 4th is 16 times 2 is 32 over 4. Yes, 32 over 4 minus and we put in the 0, we put 0 in, we get minus 0. So let me just go over this computation here. Something is not making sense. So 5 times, 5 times, there's a mistake right here. So really good to double check our work. It looks like I've made a little mistake here. I need to correct it right at this step. You see right here, this should be 2x squared. And that kind of caused a chain reaction and things were not making sense. So let me just redo this part. My apologies for that. So we get 2x squared minus x cubed. All right, let's integrate this and hopefully this will work out. So we get 5 times integral of 2x squared, that's 2x cubed, divide by 3, minus integral of x cubed is x to the 4th, divide by 4, reversing the power rule, evaluated from 0 to 2. So moment with respect to the y-axis is equal to 5 times, put the upper limit in, we get 2 cubed is 8 times 2 is 16 over 3, that is correct, minus, put the upper limit in, 2 to the 4th, 16 over 4, that's 4, plug 0 in, that's just 0. So we get 5 times, let's take common denominator, the common denominator is 3. 3 goes into 3 1 times, that's 16, minus 1 goes into 3, 3 times 4 is 12, so we get 5 times 4, 20 over 3. Coincidentally, the moment with respect to the y-axis is the same as the mass. That's not always going to happen, it's just in this case. It's just the way the numbers worked out. So x bar is equal to moment with respect to the y-axis divided by the mass. This is equal to 20 over 3 divided by 20 over 3. And of course, the answer is 1. This is the x-coordinate of center of mass. Now we need to find the y-coordinate of the center of mass. All right, let's find the moment with respect to the x-axis. Moment with respect to the x-axis by the formula is rho times integral a to b, 1/2 times f of x, all squared minus g of x, all squared, all close the bracket, dx. So the moment with respect to x-axis is equal to, the density is 5, integral from 0 to 2, 1/2 times. The upper function f of x is 2x, all squared, and the lower function is x squared, all squared, close the bracket, and integrate with respect to x. Let's simplify this. 1/2 is a constant, passes through the integral, so we get 5 over 2, integral from 0 to 2, 2x all squared is 4x squared, minus x squared squared is x to the 4th, dx. And mx, the moment with respect to the x-axis, is equal to 5 over 2. Now let's integrate, reverse the power rule. We get 4x cubed divided by 3. Integrating term by term, minus integral x to the 4, that's x to the 5, divide by 5. Evaluate from 0 to 2, apply fundamental theorem of calculus. 5 over 2 times, put the upper limit in, we get 2 cubed is 8 times 4, we get 32. Divide by 3, minus, now put 2 in, we get 2 to the 5, 32 over 5. Add these fractions, I should say subtract these fractions. So the moment with respect to the x-axis is 5 over 2 times. And take a common denominator, that's 15. 3 goes into 15 5 times 32, that's 160. Minus 5 goes into 15 3 times 32 is 96. So we get 5 over 2 times 160 minus 96 is 64. Divide by 15. If we simplify this, we're going to get, well, 2 goes into 64 32 times, 5 goes into 15 3 times, we get 32, divide by 3. So let's review what we've done. We found a moment with respect to the y-axis on the last page. That was 20 over 3. The moment with respect to the x-axis, we just found it to be 32 divided by 3. The mass is equal to 20 divided by 3. So x bar is a moment with respect to the y-axis divided by the mass. And that's 20 divided by 3 divided by 20 divided by 3. We found that to be 1. And y bar, which is a moment with respect to the x-axis, divided by the mass. The moment with respect to the x-axis, we found it to be 32 divided by 3, divided by the mass, 20 divided by 3. So we have 32 divided by 3. We flip the denominator times 3 over 20. The 3's cancel out, and we get 32 over 20. Divide the numerator and denominator by 4. 32 divided by 4, that's 8. 20 divided by 4, that's 5. 8 over 5. So the centroid x bar y bar, there's not much room here, so let me write it here. X bar y bar is equal to, the x-coordinate of center of mass is 1, the y-coordinate is 8 over 5. Does that make sense? Let's go back to the original drawing and see if that makes sense. All right, let's go back to this drawing here. So 1 and 8 over 5, that's going to be roughly about here. Does that make sense? Yes. So if your x-coordinate of center of mass, for example, was 3, that's outside the region, we know it doesn't make any physical sense. So always go back to your diagram and ask yourself, does the answer intuitively make sense? If it doesn't, maybe there was a mistake in the computations. But it looks like we did okay. All right, thank you.